right in this area down here, so we're at an area where there aren't a whole lot of sunspots happening right now. But wait about 5-6 years and this should come back up, so we should see a lot. Sort of interesting is there's also a graph showing this cycle way back. So all the way back in the 1700s. This stuff, the red, is some kind of sketchy data, but people were trying to keep track of sunspots back then. There was a big stretch of years here, about 50 years, where it looks like we kind of lost that cycle where there was a real minimum of sunspots. Kind of an interesting thing that you can learn about in astronomy and how that may have impacted not just the weather here, but impacted some cultural things. But you can see since they took more careful data, there's been a pretty darn regular cycle of sunspots. So we'll talk about that just a little bit. Trying to think of a few things here. Let me just tell you a little bit about this. It's kind of interesting. Do you know that sunspots may be why we here in the United States are beer drinkers? Not that any of you know about that, but you've heard from others.
Isn't it because we lack something?
What's that?
Isn't it because we lack something? That's why we think we'll feel better.
Because of sunspots. Anyone know what was going on weather-wise in Europe in this time frame?
It was a period of abnormally cold weather.
Yep, it was abnormally cold for a big long stretch of time here. And if I remember right, what that caused was problems growing grapes. And as things stayed cold for too long, where you could go grow grapes started getting further and further south, so you couldn't grow them in northern parts of Europe very well. Instead, what they could grow were grains. So instead of making wine, they made beer. And when did a lot of Europeans migrate to the United States?
Right around the 60s.
Right in this time frame right here, and they brought that beer making stuff with them instead of wine making stuff. So that may have impacted things. That you still see traces of that here today. Another thing this may have impacted, I know you're mostly science people. Anybody here know much about music? Not like just radio music, but like real music. How many of you know what a Stradivarius is? For real? We got to work on that well-rounded liberal arts education, huh? Nobody knows what a Stradivarius is? For real? The violin? Anyone know what's so special about a Stradivarius, supposedly? Anyway, go read some stuff.
Is it?
They're super spectacular violins made way back. Really hard to reproduce the sound that they make.
Isn't it like they were made like with a certain type of lumber or something?
Yeah, but I mean, we can still get lumber. But you're right. There's a very special wood it was made out of. And what made it special was, guess when it was growing? During this modern minimum, when there was a lack of sunspots, which may have influenced our weather, made it real cold. What happens to tree rings when a tree is growing in really cold weather over an extended period of time? They get much closer together, which makes a much denser wood. So the trees that they used in this time frame were different than the trees all through here. They were more dense than we can get now, just because of what they grew in. So that may have influenced music from sunspots. So anyway, take astronomy, you'll learn a lot more about that stuff. Where we're going to get with this is, believe it or not, what's actually causing magnetism. We've gotten close to it. We saw the other day that if we send a current through a wire, there's a magnetic field set up around it, and we figured out there's an equation to tell you how strong that field is. You have a right-hand rule to tell which way that Those field lines were gonna go around the wire. What is a current?
The flow of charges.
Yeah, it's moving charges.
Something.
So fundamentally, what causes magnetic fields, what produces magnetic fields?
The movement in charges.
It's moving charges. Moving charges cause magnetic fields. So from that, how the heck does this thing end up magnetic compared to this thing?
Well, number
So we need moving charges, right?
Number one, the stuff the pen is made out of is a very horrible conductor.
The conducting part doesn't matter. We need moving charges. Where the heck are moving charges coming from? Because I'm not sending a current through here. What are they made up of in chemistry? Atoms. And what are atoms made up of?
Balanced out charges, basically.
So a nucleus, what's in the nucleus? Protons, neutrons. What's around the nucleus? Electrons. What are they doing? They're moving, right? Very, very, very quickly. Got moving charged particles. In fact, in a very simple case, to simplify this, we looked at this the other day. If I've got, go back to our wire, I've got a current going through this wire and it's going around this way, say. There is a magnetic field set up, and what's the direction of the magnetic field like in the middle of this loop? So grab the wire with my right hand, thumb going in the direction of the current, and notice my fingers poke up through the loop. So I've just made a magnetic field that way. In fact, if I draw this quick sketch here, oops, here's my little loop, and let me try and get a little 3D perspective here. I just made a magnetic field that looks like this. And notice we've got even a north pole here, field lines coming out of the top, a south pole here, field lines coming into the bottom. We've made a little magnet. Again, it's a little more complicated than this, but we can still get an idea. I can talk about this sort of like there's a magnetic field that way right now in my little loop. In a simple sense, we can think of those electrons going around like this. Hey, that's charged particles going around like that. That's going to make a little magnetic field. So every little atom in there has a little magnetic field. So why is this not magnetic if it's got a bunch of electrons moving around in there?
Because it's an insulator, so the electrons can't really flow.
They don't need to flow. They just need to be moving around their little atom. In something like this, if one little atom has a magnetic field this way, but another one over here has a magnetic field that way, what's the net magnetic field? 0. So for most materials, all the little individual net magnetic fields, or I'm sorry, the individual magnetic fields will all end up canceling out because of the orientation. You know, there's one this way somewhere, there's one that way somewhere else that cancels it out. So most stuff's not going to be magnetic. So what's so special about this?
Okay, I get it.
We can start to line up those magnetic fields. In fact, we can start to build domains in here that have magnetic fields all pointing the same way. So as an example, let's say I've got a chunk of this thing here, and I look at some different regions, little domains like this. Normally, what's going to happen if I look at the magnetic field of each little piece, here I might have one like that, but here's the piece that's going to cancel. Here's one like this, here's a piece that cancels it. Here's one like that, here's a piece that cancels it. But what's special about this, and this is what the ancient Chinese had figured out, is they did it the hard way on a piece of magnetite and carefully going over and over and over like this on that magnetite. What they could start to do is line up these domains. So they all end up starting to point kind of in the same direction. So I've got a net magnetic field now pointing that way, and now I can actually have something that's going to be magnetic. We can do it a lot easier. All I have to do is put this into a strong enough external magnetic field, and all those little domains, the little magnetic, actually the technical term is magnetic moments, all the little magnetic moments will line up. Once they're lined up, now I've got something that's magnetic. With that, I can show you a little trick here. If you want to all come up here so you can see this. As you're coming up, why then, before we started this section that we haven't done in this room for over a year, why did I take these magnets, stick them in here, and stick them in a strong external magnetic field? What happens to the strength of this magnetic field over time, and why? It will slowly go down. Why would it go down? So there's always some thermal motion. There's always some little motion going on in there. Over time, we can start to unalign those domains, so your magnets get weaker and weaker and weaker. So all I have to do is stick them in here, and I get a nice, put them in an external magnetic field, and I get them blocked back up again. In fact, I can even do this. So I've got two magnets. You can see the north and south on there. And just to check it, when I bring this towards that compass, I'm going to point the north arrow towards it. Which needle is going to stick at or point at this thing, the white or the red? We'll just double check you guys to make sure you know this. So I'll put these away. You see which way this is pointing right now. Oops. There we go. It's pointing that way, right? Why is it pointing that way? Because that's what kind of a magnetic pole is that up there? That's a south pole. Remember, magnetic field lines come out of north poles into south poles. That compass needle will point right along those field lines. So those magnetic field lines that we're standing in right now, so we're immersed in a magnetic field due to the Earth, are pointing that way. And that compass needle will point right at it, right along those lines. So if I poke the north pole at that compass, which way is that going to spin around? So field lines point away from north, compass needle will point right along those field lines. So is which color on that little pointer is going to be closer to the north pole, the white or the red?
White.
The white, okay. So there's the north pole, and sure enough, there's the field lines coming out like that. So same with this one. Just to check it, north pole, yep. I can actually do this. I'm going to flip them, because I'm going to put them in here the wrong way. And put them in a strong external magnetic field, and that will realign those domains. So that if I poke the north at the compass, I just flip the poles. Try this one. I just flip those poles. I just realign 0 leads. So there's nothing special about what was written on there. It's just how you want to do this. So let me put them back again. So again, put them in a strong external field. Line up the domains. See if I can come back. So north pole, it's back again.
Why do you have to make a connection between the two magnets?
Well, we'll see that here in a second. It's directing the magnetic field.
Oh, okay.
And notice I alternated the way these were, and it's sending a field like that. Okay. So nothing special about what was written on those. I can set those up however I want. So I mentioned we're sitting in a magnetic field right now. So what the heck is causing that? So we're sitting in a magnetic field. Only compass tells you that. So what causes that? So what makes magnetic fields in a real fundamental sense? moving charges. So what must be inside the Earth? Moving charges. And hopefully you've had enough geology to know we've got some molten stuff down in there, that there is some liquid down inside the Earth. And we do need that, so as long as that liquid's moving, we've got a chance for charges to be moving, which means we can generate a magnetic field, which is great because that protects us from all those charged particles coming from the sun. So we saw how charged particles enter magnetic fields, there's a force on them, so it keeps us from being bombarded by high energy particles from the sun, because those are charged particles. As far as the actual mechanism that's producing the magnetic field, that's something that hopefully you guys will learn in your lifetime, because that's a big area of research. There's some good models, some good speculation. We know there's got to be moving charged particles, but exactly how they're moving, they're still working on that one, coming up with different models for that.
So we don't really know for sure.
Not the details. Not
Yeah,
the details.
the
of it.
exact details.
In other words, yeah, there's fluid that's moving, but why is it moving? Is it convection currents because the core is hot? Is it coming from larger high-density atoms that are sinking down, lighter atoms floating up, and that's causing some motion? So there's different models out there trying to describe that. Even more curious, if I've got, again, in a simple case, if I've got charged particles, we'll put them in here again because this is a little easier, going around like this, I've got a certain direction for a magnetic field. It's that way, like the little picture there. What happens if I flip the direction of that motion? So I grab like this, so fingers poking down like that. I flipped the direction of my magnetic field. Mentioned this the other day. Yeah, that's geographic north, but a magnetic south, but it hasn't always been that way. Over geologic time, our magnetic poles have flipped back and forth quite a few times. What, in a simple sense, would cause that flip? I've got charged particles going one way, or charged particles going the other way, it's going to flip the direction of that magnetic field. A place we do see that is actually on the sun. So what are sunspots?
Is magnetic moments on the surface?
There are places where the magnetic field is actually coming out of the photosphere. So I have to be a little careful. The sun doesn't have a surface. It's not like if you went up there and stepped out, you'll be walking around on a surface.
Oh, right.
It's just that it's emitting electromagnetic radiation, we'll talk about later in the semester. What appears to be a surface is just the part that's in visual wavelengths that we can see with our eyes. So it looks like a surface to us. And what you're seeing is where the magnetic field lines are poking out of that photosphere, which makes for a slightly cooler area. And being cooler than the surrounding part of the photosphere, it makes it look dark to us. So you see these little spots. And the more active the sun is, the more sunspots you have. And what happens is, every 11 years or so, you see the sunspots die off, then they grow back up, and they die off. And what you're actually seeing is a consequence of the magnetic field of the sun flipping back and forth like that. And the sun's a little bit easier to picture because it's a big ball of gas, so you can picture things swirling around in there, and maybe they go the other way. But you can kind of see that with that sunspot cycle, a little bit like you see with the Earth's magnetic poles flipping back and forth. But again, fundamentally what's causing these magnetic fields are moving charged particles. With that, let's take a look at something else here for today. Pretty amazing equation. I hope you start to get an appreciation for what math can do. Because this one's really spectacular. So check this out. This is a super amazing equation. And I'll do it without the calculus version. that thing there. That says so much in such a compact little form. What it's called is Faraday's law. What it tells you, those are compact instructions on how to make electricity. And it even tells you the direction of the current you're gonna make. That's all in that little formula right there. It tells you exactly how to make electricity. And if we step back, I bet you guys can even figure most of this out. This is about the only thing you're not as familiar with. This is got an old terminology. It refers to something called EMF, or electromotive force. What it really is for us, that's voltage. So you can think of this instead as voltage. And if you remember from Ohm's law, that's also another way to say current. That if I've got some resistor and I apply a voltage across it, I get a current to go through that resistor. So ultimately, this part here says you're gonna get a current. Here it is right there. And how do you get a current? Well, let's look at some pieces here. Let's start with this guy right here, because we've seen something like that before. That's magnetic flux. And we saw that concept before. Well, I've got some area. Let's use this guy here. Here's some area right here. And I place this in a magnetic field. And I'll use my fingers to represent some magnetic field lines. And right now I've got some field lines going through that area. Magnetic flux is essentially a measure of the number of field lines going through that area. So this part here is just field lines through an area. This part says a change in those field lines. Let's see, we ran through this before. Let's see if you remember this, because we talked about electric flux a while ago. The only difference now is we're talking about magnetic field lines instead of electric field lines. So how can I change the magnetic flux through this area? So right now I've got, let's do it this way. Right now I've got 2 fingers through there, 2 field lines through there. What are 3 ways I can change the flux through this area? What's that? Size of what? Of the area. I can change the size of the area that my field lines are going through. If I made that loop of tape bigger, I could get all 4 fingers through there. So one thing we can play with is the area. It's another thing I can do.
The strength of the electric or the magnetic field?
I can change the strength of that field. And remember, when we draw these field lines, the spacing of the field lines is relative to the strength of the field. So if I make my field stronger, I'd have to put my fingers closer, and oh, now I get more fingers through there. I get more flux through there. So the strength of the magnetic field influences the flux, and what was the third thing? The orientation of these two. This area, which would be perpendicular to the, like the face here, so the area points like that. Here's the field lines. Notice if my area and my field lines point the same way, I can get the most fingers through here. If the area and my field lines are perpendicular, so again, here's the area vector, so to speak. Here's the field lines. If they're perpendicular, how many fingers do I get through? None. So how, in a nice compact way, do I say I get the most flux when they point the same way, I get no flux when they're perpendicular, I get something in between when that angle is somewhere in between, which is lots of words. Almost. I can't just say angle. I've got to say some way I get the most when they point the same way, none when they're perpendicular, and something in between when they're in between those two. But it says all that in a nice compact form. You guys only know 3 trig functions right now. Sine, cosine, or tangent? Which one of those, when theta is 0, is 1? It says they point the same way, I get the biggest. Yeah. So there's magnetic flux. There's 3 different pieces there. I can play with the magnetic field strength, I can play with the area, I can play with the orientation between those 2. Again, this tells us how to make electricity. What does this say I need to have happen with that magnetic flux? What does this say is happening to the flux to get a current, to get
Has to vary
electricity?
with time.
What's that?
Has to vary with time.
I've got to be changing it. Okay? That's exactly what that says, just like you said. This says I can get electricity if I change my magnetic flux. As long as that flux is changing, I'm going to get a current. How can I change it? I've got 3 different ways. As long as my magnetic field is in the process of changing in that area, or as long as my area is changing that's sitting in the magnetic field, or as long as I'm changing the orientation. As long as any of those are in the process of changing, I'm going to get a current. How about this piece? So again, this part says, change my flux as time goes on. That's just, over time just says change it. As long as it's in the process of changing, I'm going to get a current. So what's up with this piece? This said I need an area. This part said I need some resistance. At least at this point. We'll see that's a little bit different later. Here's a wire. As long as I make a loop, I've got an area. As long as I have a magnetic flux in this area that's changing, I'm going to get a current in this loop. So this says not only do I need a loop, but how come it's an N? How can I get more and more and more current if I do the same change in flux? What do you suppose N actually really is? What do you suppose it really is?
Some sort of integer multiple?
Yeah, it's the number of loops that you have. The more loops I have, the more current I'm going to get. I need at least 1 loop, but the more the better. So this is just the number of loops we have. Need at least 1, but if I have more, I'm going to get more current. And then one more piece, a negative here. That little negative is Lenz's law. That tells me the direction of the current. And what Lenz's law says, again, that's an indication of the direction of the current I'm going to get. So here's what it is in words, and then we'll go through some examples. When you make a change of flux inside a loop, and this is going to take a lot of words. When you make a change of flux inside a loop, you're going to get a current in the loop. The direction of the current is going to be set up to oppose that change that you're making. That's the negative part. It opposes the change you're making. Let's actually run through some examples, see how that works. When you do problems using Faraday's law, don't worry about that negative. That's just a reminder of the direction of the current. So you kind of leave that negative out of there when you're actually doing homework type problems. But let me run through some examples and let's see what would happen here with directions. Let's do this one. Let's say I've got some wires like this. Here's a little resistor, maybe a light bulb or something, so I can see if I've got current or not. And then what we're going to do is put a little sliding conducting bar on top of these wires. So there's contact there. And what that's gonna let me do is I can take this little bar and slide it back and forth. Let's drop this whole thing into a magnetic field. So let's have this be a magnetic field into the board. And I'm not plugged into anything or anything like that, but all I'm gonna do is take this bar and slide it that way. While it is sliding, will I get a current in this loop? And if so, why? What's changing? I'm making the area bigger. So again, I have three choices here. What I'm doing when I'm sliding that bar like this is I'm making that area of that loop bigger. While that bar is sliding, my area is changing, so I will get a current. That's the Faraday's law part. I'll actually get a current in that loop. And you guys will get a chance to see that here in a bit. Now the question is, what's the direction of the current? Is it gonna be clockwise or counterclockwise around that loop? That's the Lenz's law part. So let's see how that works. And I'll try and walk you through kind of an easier way to do these. So here's a good way to do these, is start with looking at what your situation is to start with. I'm gonna use this guy, I guess is my little problem. So I've got an area. In this case, I've got a magnetic field going which way before I do anything? It's going that way, right, into the board. So here's what I'm starting with. Field into the board. With the change I'm making to make my current, is my flux increasing or decreasing? Am I getting more or less field lines in there with whatever change I'm making? Am I getting more or less field lines by what I just did there? I'm getting more. So I've got a field into the board and it's increasing. How do I oppose that change? Notice when you get a current, that's going to make a magnetic field. That current is going to try to oppose that change I just made. Because we're making a current, the only way it can oppose is by adding flux. So let's put that all together. My field's this way, it's getting bigger, bigger. How can I add flux to oppose that? Which way do I need to have my flux going? If I've got more and more this way, how do I balance that off? I need more and more that way. So my current is going to make a flux or magnetic field that way. And what kind of current does that? Take my right hand, poke my fingers through like that, and which way do we wrap around? That way. So that will induce a current like this. Or on the board here, this will make a current that goes that way around this loop. If instead, I mean, it should be intuitive which way it is, but let's see if we can walk ourselves through this. If instead I slide my bar this way, are we really going to get a current to go the opposite direction now? Let's see how that would work. So I've got flux into the board. Is it increasing or decreasing? It's decreasing now because I'm making my area smaller. My current I induce is going to add some magnetic field lines, but it wants to oppose that change we're making. So if my field's this way and it's getting less and less and less, how do I try and get back to where I was? I need more and more and more that way. What kind of a current will give me more and more that way? Stick my right hand in there, fingers like that, and sure enough, there's my thumb going around the opposite way. So yep, we're going to get a current going the other way now. Let me try you on a different one here. Let's say I've got a magnet and a loop. We'll make this a conducting loop. The tape actually works better, but for props, but this is a conducting loop, like a wire. And let's do this. I'm going to point the north arrow, or the north pole, at the loop and do this. As my magnet's moving, will I get a current in this loop, and if so, why? I've got three things that could happen here. So as I do that, which thing am I changing there? I'm changing the magnetic field. It's getting stronger, stronger, stronger as this gets closer, 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 which puts more and more field lines in there. So by doing this, I'm increasing the flux in here while this is moving. As long as I have a change in flux, I'll induce a current. Question is now, what's the direction of the current? Is it that way or this way across the top? So let's try and walk through this one. So I pointed the north pole towards it. So which way are the field lines going through my loop? Out of north, so that's that way. As I come closer and closer, is my flux getting bigger or smaller? Bigger. I'm getting a stronger field. So I'm getting more and more flux that way. How am I going to oppose that? Am I going to try and get back to where I was? I need some flux that way, right? So just make sure you do it with your right hand. If I stick my right hand through like this, my current will go that direction across the top. So if you go step by step like that, it's not too bad to figure out the Lenz's law directions and things. With that, let's take a look at some magic tricks here. Got a little device here. This is the commercial version that works really well. This is a scary student-made version that's dangerous. But I kind of like it because you can see things a little bit better. So what you have here is just a bunch of loops of wire connected to this, which means when I plug it in the wall and do something, I can send a current through these loops. Can you tell what that is poking out the top? You want to recognize those? Not even. You want to recognize that?
Are they welding sticks? I can't see.
Good, when you find out, John. They're coat hangers. They're old wire coat hangers that the people that put this together cut. Like the bottom part of the wire coat hangers. So they're coat hangers poking out. And I've got a little aluminum ring. And a little aluminum ring is going to go over there. This is the exact same thing. Here's the ring. Here's the loops of wire I'm going to send a current through. And it's just a little fancier, but you can almost see almost like coat hangers in there. So if you look in there, it's like the little coat hangers. See it on there? So it's just a fancier version, but it's just like that. So my question is, when I turn this on, what's going to happen and why? So let's walk through this. Right now there's nothing happening. It's not plugged in, nothing's going on. Is there any magnetic field other than the Earth going through this thing? Nothing's happening, right? There's no flux. When I turn current on into the little wires here, we looked at that before. That's basically a solenoid. Bunch of loops of wire, all loop the same direction. When I turn a current on in there, what am I going to make? I'm going to make a little electromagnet. And let's say the direction of the current, let's say, is going like this at this instant. So that's going to give me a magnetic field. It looks like this. So I'll end up with a north pole here and a south pole here. Well, wait a minute. Before I did anything, I had no magnetic field. When I turn that on, all of a sudden I have a magnetic field. How does it go from nothing to something?
It
has to change.
It's gotta change. And I've got a loop. Which means, as that magnetic field goes from 0 up to whatever it's gonna be, I've got a changing magnetic field or changing magnetic flux inside a loop. And this is a conducting loop. So I will get a current in the loop. You're all okay with that part, right? I'll get a current in the loop while that flux is changing. And the direction of the current will be set up to oppose that change. So let's say here was my arrangement here. So I've got, I'm going to switch to something a little bit bigger. So let's say I've got flux this way, and it went from 0 up to something, so I'm changing the magnetic field inside my loop. What's going to be the direction of the current in this loop? I'll let you guys figure out. Is it going to be, we'll use the part of the tape pointing towards you, that way or that way?
Around the circle.
Right. So, flux is this way, getting bigger, bigger, right? How do I oppose that? I need flux this way. What kind of current's going to give me a flux this way to oppose my change? That way. Okay? So I had a magnetic field pointing up that induced a current like this, right? Everyone okay to there? Well, if I do that, if I've got a current like this, I just made a magnet out of this. What's the magnetic field like inside here? We just said that, right? Grab like this, I've got a magnetic field pointing that way, right? What kind of pole is this down here? North or south? What pole is this here? What pole is this here? Field lines come out of north into south. Is this north or south? Which way my fingers are pointing? Out. This is north, right? So wait a minute. We're saying I've got a, you draw it on there. Let me draw it up here so it shows up better. What'd you learn back in about kindergarten? What do like poles do? They repel. So what should the little ring do? Let's find out. So that says it's on. When I flick this switch, it'll actually send current into the little wires. So what should it do? Ready? Yep. Do that one more time. So as soon as I send current in here, I get a change in flux in that loop, induces a current in the loop to oppose that change, end up essentially with two like poles facing each other, and it will, for a commercial version, shoot it up pretty good. What was that? The scary one?
Yeah.
You guys do know that there's a fire extinguisher in there? And somebody said they knew how to use those heart starter things? You guys know where it is?
Yeah, oh,
How
I'm
much-
certified in first.
How much time do you have? 2 minutes
Before
before I'm dead?
you're dead.
Brain dead.
Brain damage comes after.
We'll wait.
Lack of oxygen.
So one of the issues, it's got the wrong kind of switch. This is off. So I have to hold it in. And it will heat up super fast. So it won't be as spectacular, but it should still work. Ready? So it'll still shoot it off. So it does actually work.
I think I smell something burnt.
That's my fingers. Actually, I will talk about something that I will not demonstrate a second time, because I did do it once.
Let me see it.
And I do learn from my mistakes.
They built something on it.
But here's my question with this device. If instead I hang on to this, turn it on, then let go, will it fly off or not?
Yes.
No, because it's no.
And if not, why not? If so, why so? So again, what I would do is, rather than, like I did, hang on to it, turn this on, then let go.
Well, I mean, if you're waiting till after it's turned on.
I'm gonna wait till after it's turned on before I let go.
Yeah, the current is already, not sure what the right word would, just started up, I suppose. It's no longer
Still gonna
changing.
fly off, it's just gonna hurt.
So, will it fly off or not?
Well, because the magnetic flux is no longer changing, because the current is now constant, there wouldn't be any.
So again, remember what this is gonna rely on is I've gotta have a changing magnetic flux in this loop to turn this, to get a current in this, to turn this into a magnet. So if I hang on, turn it on, wait, then let go. Is it coming off or not? It's a trick question. Yes, it will. But wait a minute, I thought we said we needed a changing magnetic flux. What's coming out of the wall? What kind of current?
I see what you do, what you're doing.
What kind of current comes out of the wall?
Alternating.
It's alternating current. What's alternating current? It's continually going back and forth, back and forth, back and forth. If I'd sent direct current into here, let's say I hooked it up to like a car battery and sent direct current, then yeah, if I hung on to it, once this has the current going in it, I have no more change in flux, and I need the change. If it's an alternating current, the current itself is continually changing. So it doesn't matter if I hang on or not. It'll still pop off, and I have witnessed it. Do you know why I'm not gonna do it? Yes.
Didn't you say you would electrocute yourself?
That puts a current through here, that bad boy heats up and heats up fast. So I got my fingers scorched one time I tried to do it.
What?
So-
Did you
so-
just want to try it?
Well, yeah, I thought, well, I know it should happen. I know it should happen, but I thought, oh, this will be one of those like trick questions, because you'll forget that it's actually alternating current coming out of the wall.
Yeah, and then all
But
of a sudden the smell of
it
burning
did,
flesh
yeah.
fills the
So-
room.
It will come off.
Can you just do it once more
No.
for the video?
No. Let's see, how about this one? Let's see. Let's do this and then we'll take a break. We'll do a magic trick.
No, I know what you're gonna do.
All right, so this one. No trick here. It's just an empty tube. So nothing special about the tube, it's just an empty tube. Okay? And I've got two things here. And just so you verify there's nothing tricky about these either. Same mass. So, same mass. And I didn't talk to you before class and like you're one of those like plants in the crowd or anything. Okay, so all I'm gonna do is drop them through the tube. So take this one, and like you learned in first semester physics,
What goes up
Options.
should go down.
but like you learned in second semester physics, It'll come
I love that.
So what's up with that?
We've got all the math right here.
Yeah, it says it right there. It's obvious. So how come one acts like a little first semester weight and just drops right through?
The first one's not a magnet.
But the second one drops like a second semester physics weight. So yeah, what's the difference between the two?
One's magnet, one's not.
This one's got a magnet in it. So how come it took so long? This is not magnetic. It's just an empty tube. Well, let's take a look. So this has a magnet in it, so there's a little magnetic field. And as I drop that, let's take a look at one piece of the tube right here that I've marked with tape. There's a little loop. As I drop this guy, there's a magnetic flux going through this part of the tube. Let's say again, this is the North Pole pointing down. So as this falls, I've got an increasing flux right here. As long as this is falling and I have an increasing flux, I get a little current right here. Fortunately, not enough to burn me this time. I get a little current there, right? What's the direction of the current induced right here? So north that way, it's increasing. I need to oppose it like this. So I get a current, if I stick it like that, I'm going around like this, right? In fact, what have I done to this little piece of the tube right here? If I send a current around that way, I've just made the top part of the tape a north pole, the bottom part of the tape a south pole, right? And what happens is I'm dropping a north pole towards that north pole. They repel each other, which slows this guy down. Does that part make sense? So that's going to slow that down. So it's like I'm making a north pole down here below it that's opposing that. Why doesn't it then just stop? Why wouldn't it just stop there? Because here's a north pole, here's a north pole.
They don't need velocity.
Why not just stop? What do I need to have happen here to get a current? I need a change in flux. What happens if this stops?
There's no more current.
I have a flux, but it's not changing anymore. If it's not changing anymore, what just happened to my current? It stopped, so what happens to my weight? Oh, now it can get going again. In fact, what ends up happening is this falls at a terminal velocity based on that current that's being induced. If it goes faster than that terminal velocity, I get a bigger current that opposes more. If it goes slower, I get less current, now it can go faster. So it finds a terminal velocity. In fact, one of your take-home test questions, you're going to be dealing with that concept of this magnet falling in something like this and reaching a terminal velocity. So, kind of make sense? As we take a break here, let me try something real quick, because I think if I remember right, this is kind of good. But let me test it. So, here's my little stack of neodymium magnets. And if I remember right, if you want to try this, this might look kind of cool. With that in there, you can't really see through, but with this you can. Just be careful with those neodymium magnets because they're pretty strong. So be careful what they're near. But if you do this where you can see down in there and drop this guy in, you'll actually see it kind of float its way down. So if you want to play with this and we'll take a break, go ahead. But let's take a break for about 10 minutes. Let's do just a couple more examples here of uses of Faraday's law. Got a picture here of an electric guitar, in case you don't remember what they look like. Any of you familiar with electric guitars or play them or anything like that? You know what these things are? Not the strings, but underneath them. So your explorations of life ended with battery licking and Play-Doh eating? I shouldn't pick on like that. Those are pickup coils. It's really interesting how electric guitars end up making sound. Here's another picture of pickup coils. They look like this, and the strings would be over the top of them. And a basic version is like this. It's basically a magnet with a bunch of wires wrapped around. Go off to something. And at this point, let's say this magnet is set up like that. So it's just a permanent magnet like those bar magnets. And then we're going to stick a guitar string over the top of it. Anyone know what those strings are made out of?
Metal wire.
Yeah, they're metal wires. So what happens when I take that guitar string and I pluck it so it vibrates at some frequency? With an acoustic guitar, that's going to make sound by vibrating the air, and thus that air, the compressions and rarefactions of the air get to your eardrum does like that, and you can interpret that as a sound based on how that string's vibrating. Different vibrations, different sounds. What's going to happen here though? So I pluck that string and it starts vibrating. So we sort this out. Got to figure out what's the function of all this stuff. What's the function of this permanent magnet? How come this is metal? What's up with the wires here? And how is this going to do something for us? So let's pluck the string. And again, to make it simple, let's just say it's vibrating up and down like this. Well, let's see. We've got loops of wire, right? So we've been talking about loops of wire. And we talked about how we're going to get a current in those loops. We need some kind of changing magnetic flux. So how are we going to get that? So we are going to get a current in those loops, but how are we going to get it? Let's back up a step. What is the function of this magnet here? Let's see, you guys did that way back. Get something real quick. Here's a magnet. Here's a metal wire. What did that magnet just do to that little paper clip? Magnetized it. What's the function of that permanent magnet with regards to that metal string sitting above it? Magnetizes it. Turns this part into a little magnet. And how are the poles oriented? It's got field lines like this. So makes a little magnet. Okay. Now let's pluck that thing. So my little magnet's going up and down like this. What's that doing in the loops? It's changing the magnetic flux in the loops, which means I get a current in those loops. And the current is set up to oppose that change in flux. So here's one of my loops. Here's my little string going up and down like this. As the string goes down, I get a current one way. As the string goes up, I get a current the other way. That make sense? In other words, what I produce is an alternating current. One way, the other way, one way, the other way. And this current that's coming out of these wires going one way, the other way, one way, the other way, at what frequency is that going back and forth and back and forth?
At the frequency the string
At the same frequency that this string is vibrating. Notice what we just did. We took a vibration of a string, converted it to an electric signal, converted it to a current whose direction matches the vibrational frequency of that string. Or that alternating current is going to match that frequency of that string.
And then a computer can interpret that as
Then
sound.
we can do some things with it. Once we've got that vibrating string converted to an electric signal, we can play with that signal. We can put amplifiers and other things in here. We can distort it if we want. For us, let's keep it nice and simple. Let's see how we're going to produce sound out the other end. What we're going to do is send that electric signal now to a speaker. And I've got some little cheap speakers here. So here's a little speaker. And what this guy's going to do is that little diaphragm there. You guys have all seen speakers like this, right? That little diaphragm goes in and out, in and out, and in and out. That little in and out stuff makes the air go through the compressions, rarefactions. That sends that to your ears, and then you hear that. So it's doing it by vibrating this. Let's take a look at what's actually in these speakers. I tore one apart so you can see what's in there. So I'll pass this around as I draw a little sketch here. What I want you to watch for is I put a paper clip in here so you can see there really is a magnet in there. So you'll see the magnet in there. There's actually one out here too, I guess. So you'll see the magnet. Inside that magnet, you'll see a little sleeve. Try not to pull it all the way out, but I pull it halfway out. There's a little like cardboard sleeve right there. And if you look close, you'll see there's a bunch of loops of wire. What I tore out was this diaphragm was attached to the end of this little sleeve. So as that sleeve, and you'll see it can kind of go in and out of a little pocket there, as that sleeve goes in and out, it would have moved that diaphragm in and out. Excuse me. So I'll pass this around so you can see that up close as I draw a picture of it. And we're going to look at it a few different, from a few different perspectives to see how that's actually going to work, how it's going to take our signal here and turn that back into sound. So let's see, here's one picture. I'm going to try and draw. So this part is the magnet. Let me do it like this, sorry. This part's the magnet inside there. Here's the sleeve that's pulled all the way out in my little picture here. Here's little wires wrapped around it. Actually, this way maybe. There's little wires. Here's where that diaphragm would be attached, except I tore it off right here. And then this sleeve goes right into this little opening here. So I'm going to push that in there. Let's take a look right straight head onto this thing and what this is going to look like. So that magnet looks like this. Here's the part that the paper clip was sticking on. Here's that opening that we're going to drop our sleeve with the wire wrapped around it. We're going to drop that in there. And then this is the other part of the magnet out here. What that shape forms is a magnet like this, where that inner core is the North Pole, the outer core, say, the South Pole. So they're opposite poles. We'll say, just for argument, that the inner part's the North Pole, outer part's the South Pole. Notice what kind of magnetic field that makes then in that gap. Field lines run from north to south. Here are my field lines. And that's what we're going to drop our loops of wire into this field. So here's, say, one of the loops right here of wire in there. Let me redraw that loop next to it just so the picture's not so busy. And let's see what's going to happen. Let's say what I did is I sent a signal, maybe from something like a pickup coil. I sent a signal with a current in a direction, one way or the other way. Let's say at this instant, the current that I sent in those loops came in and is going around this way, clockwise in my picture. And let's look at some locations. I'm gonna look right here, and I'm gonna look right here. So at this instant, at this location in the loop, I've got a current going that way. So I'm right here right now. I've got a magnetic field this way. Therefore, I've got a force on that part of the loop. What is the direction of the force on that part of the loop? If I've got a current that way, magnetic field this way. You were right, by the way. Which way? That way. If you don't get that, let me know. Yeah, that's exactly what you do. You hold your hand like this. Thumb in the direction of the current. Fingers in the direction of the field lines. And which way does your palm push? Out. So I've got a forced out. So I'll draw it like this. How about on the other side? Over on this side of the loop. So again, my current's going clockwise at the moment. So over here, it's going this way. It's sitting in a magnetic field because of the shape I dropped this in. The magnetic field is this way on that side of the loop. So what's the direction of the force? Out. So if I send a current into my loops of wire that I've dropped into this magnetic field, and in this picture, in this orientation, my current's going clockwise, and I attach a diaphragm to the end of this thing, what's that diaphragm gonna do when that current goes that way? It's gonna get pushed out. What's gonna happen when I flip the direction of the current? You can walk through if you want to figure that out, flip the direction of the currents. It's gonna get a force into the board, so what happens to my diaphragm? Goes back in. So if I do nothing special, but again, one advantage is we can do things in between, but let's say I didn't do anything in between my guitar string and my speaker. Watch what happens. I pluck my string, I convert that into a current that's alternating back and forth at the exact same frequency this is vibrating. Send that electronic signal to my speaker. When that current gets to those loops, it's going back and forth in those loops at the same frequency that my original string was plucked, which is gonna make my diaphragm do what? Go in and out and in and out and in and out at that frequency. And now we get sound made that's gonna match the frequency of that string. But again, the nice thing is we can play with that signal between here and here if we want to do something else with it. But in a simple case, we've just reproduced that vibration of the string all the way to a speaker, but we did that sending it with an electronic signal. Does that make some sense? So that's basically how a speaker works. Here's another interesting one. Let's see what I got here. Let's get one that shows a little bit better. There we go. This one does. You guys know how these little strips work on the back of your credit cards? And before you ask, I don't know how the chips work. But you know how the strips work? They're actually pretty simple. In fact, you get a clue every time you use this at the gas station of how they work. What does it tell you when you go to the gas station and it says insert card, then what does it say? How does it tell you to pull? What does it say? It says pull quickly or quickly remove, right? So let's see what's up with that. It's actually some relatively old technology now. You do know there's information coded on there? somehow. So let's see how you would actually code the information. So here's your little strip. So it's like that, trying to draw it sort of through. And to code the information, all we're gonna do is have a magnet, like this. And let's put some wires around up here. Bunch of loops. And let's make this some sort of iron core. And the trick with this tape is this is a magnetic tape, and the way we're going to store information on here is magnetically. So how does that work? Let's send a current into that loop, those loops of wire, so whatever direction we pick. So we send a current in there, we make a magnetic field in the loops, right? So what's the function of that iron core? We actually saw that right here. What's up with the coat hangers? If the coat hangers were not there, and I just sent a current into my solenoid here, all these loops of wire, I would get a magnetic field, and if I were to try and draw the magnetic field lines, they're going, let's say this is the North Pole up here, they go straight up like this, and what happens when they pop out? They go like that. You know what these metal coat hangers do? They direct that magnetic field, so rather than the field lines go out like this, I can continue that magnetic field up like that, and then they'll go out. So what these guys do is they'll direct those magnetic field lines. Guess what that iron core does? If that were not there, I'd get a magnetic field in here, the field lines would be going like that. But with that iron core in there, I can direct those field lines so that they come around like this. So let's say I send the current a certain way so that like this would be the North Pole. What I can do is send those field lines down like this, so this now becomes a North Pole here, South Pole there. And I get my magnetic field. Let's draw a few of the field lines like this. And then at that instant, let's lay this magnetic tape underneath there. The way this tape is designed, it was kind of like those bar magnets, where if I put this tape in an external field, I've got little domains in here that will line up with that external field. So at this instant, I've got little pieces in there that line up like this. Now let's move the tape a little bit. So this part is now over here. And let's flip the direction of the current up here. If I flip the direction of the current, it's going to change the direction of these poles. It's going to change the direction of this magnetic field. And it's going to change the direction that these guys, these little domains, are going to line up on the tape. So all we have to do to code information is slide the tape across and switch that current back and forth. How many of you are at least vaguely familiar with the binary system of counting? What is it? Instead of 1, 2, 3, 4, 5, 6, 7.
It's just 0, 1, 2.
It says zeros and ones, right? What's nice about a binary system, computers like this kind of stuff, it's one way or the other way. It's on, it's off. It's a really easy way to keep track of things. Notice what we have here is a really simple way to code things in a binary system. We either have a magnetic field pointing that way or that way. So we can send a binary type signal in here, alternate our current back and forth, lay a pattern on this tape. And when I walk away, there it is sitting on the tape. Just like when I walked away from my bar magnet, I fixed how those domains were set up in that bar magnet. I could have changed them, in fact, we did change them, then we put them back, now it'll sit there like that. Same thing with the tapes. By the way, have you heard not to get your credit cards near strong magnets? Do you know why? Because you can, if you get these near strong magnets, you can start to realign these different domains. So again, there's a pattern laid on here that's coded information about you or your bank or something like that. So that's how it gets on there. Now the question is, how do we read that? So how do we get that information back off again? The reader is this basic same setup. So again, what we had was an alternating current, and we laid that pattern down magnetically on a strip of tape. Now let's take that strip of tape with this little pattern, run it underneath here. So at this instant, I've got a little magnetic piece right there that makes a little magnetic field, say this way here. This iron core will direct those field lines up into my loops of wire. I can get a current in those loops of wire as long as that magnetic field is changing. Or I should say the magnetic flux in those loops is changing. So as I slide that strip, these little domains are sliding by there. That's changing the magnetic field here. That's getting up into my loops. That is then inducing a current in there. The direction depends on how I've changed that flux. And what I can do is reproduce the original electronic signal of alternating current. So what's up with sliding fast? Shouldn't you give the reader time?
The faster you slide it, the more current you generate.
Says it right there. The faster you change that flux, the more current you're gonna get, which makes it easier to read. So when you zip it out, what you're really doing is making more current by making a quicker change in flux. The faster that change, the more current you're gonna get.
And you don't really have to worry about it picking it up or not, because these things are computers, they work fast.
But you need enough current. If you go too slow, you may not be inducing enough current for the reader to read. So zip it fast and they're happy.
Yeah, but it's kind of difficult, what I was trying to say, it's kind of difficult to do it too fast.
Yep. No, they're pretty good at it. So that's basically how that stuff works. Any questions on that? It's probably a good spot to stop for today.